Hi everyone. I hope you can hear me.
Yes, sir.
Okay. Yeah. Let me share my screen. Okay. I guess you can see my screen and the mouse
Yes, sir.
pointer. Okay. So how was this week's lecture for computer vision? It's week 9. Yeah. Okay. We already finished two-thirds of the course. We are in the last one-third phase of the course. Okay. How was this week's lecture? Easy, hard.
And some were not understandable, medium, sir, medium level.
Okay. Okay. Yeah. I mean, this topic was relatively harder than others, that's for sure. Okay. We'll try to cover as much as possible. Yeah, for the last session that we were discussing, I was talking about the max operation. So, max operation is non-linear when you consider the additivity part. So, the linearity part contains, linearity contains two parts. One is homogeneity, which is just the scaling factor. Although if you scale all the elements, the max won't change. The max will be scaled appropriately. But if you change the, but if you add two different uh, numbers and then take individual numbers and take the max of individual numbers, they may not be the same. So, so max is a nonlinear operator there, which I guess we were discussing in terms of nonlinear color spaces. Okay, yeah.
Yes, sir.
So, yeah, okay, yeah. So we'll just switch to this week's question. Um, okay, consider a hyperbolic paraboloid representing a parametric surface xuv as uv and uv with u and v given some values with respect to t, and we need to find the first fundamental form coefficients. Okay, it seems daunting by the way, but it's not really that hard. Let's first understand what is this. Okay, what are we trying to do initially? I mean, why are we going for all this first fundamental form and second fundamental form? What's the intention to do it? So we are trying to understand how the surfaces are based on the local geometry, and specifically speaking, we are trying to understand the curvature of a surface at any given point on the surface. So what do you mean by curvature? You would have seen three to
Um,
four formulas in the lectures. Yeah, yes.
Maybe having some objects like with some shape.
Now, what is curvature? I mean, there is some object with the shape
Curved.
which we are trying to capture using the range cameras, right?
Yes, sir. Object with curved edges.
Yeah. What do you mean by curve?
Curve.
Curve is just some one-dimensional. Uh, Curve is a one-dimensional thing, right?
Yes, sir.
It just has one independent parameter, so that's why I'm saying it to be one-dimensional. So now when you embed it into two or three dimensions, it may not be straight. It might be, uh, as you said, curved. I mean, it can take different forms and it may not be straight line. That's all I mean to say. So that's a curve. And what do you mean by curvature?
Closed curve. Like,
No,
like the.
curvature is
Okay.
some measure, right?
Mesh.
So what are we trying to measure there? So I mean, just see this figure. What do you what can you say about this part? Maybe let's change the marker. Okay. What can you say about this part? Can you say that curvature is high or low? Intuitively speaking, don't go with maths, okay?
Low.
Okay. And what at this point?
I.
Okay. So you are saying that curvature is high here and curvature is low. Okay, but so if I give you a flat region, then what's the curvature?
0.
I mean, not mathematically, just
Okay.
intuitively for now.
Very low.
Yeah, I mean, it's like it doesn't have a curve. We say it like that. So mathematically,
Yes,
yes,
sir.
it will turn out to be zero when you apply those formulas. So, so given this idea of, I mean, given this intuitive idea that here curvature is high and curvature is low, we would like to see it slightly more geometrically before going to maths. So, so what is the normal here, for instance? Assume that this is normal, although it doesn't look like. So this is the first normal. I mean, at this specific point, if I draw a normal, it looks like this. And if I now slightly change the point, for instance, it might look like this, right? Normal to the point on the curve. Similarly, if I draw a point here like this, I mean, this would be the normal to the point. And if I go here slightly uh, adjacent to that point, some other point, you can see that that normal will almost be same as that of the this normal. So these two will be very close to each other. Do you agree with that?
Yes, sir.
Close to each other in terms of angles. So the dot product will here be nearly 1, and the dot product here will be less than 1. Do you agree that?
Yes, sir. So just a clarification. Now, normal is perpendicular line, right, sir?
Yeah, yeah, yeah.
Okay.
Perpendicular to the point. I mean, to the whole, or rather perpendicular to the tangent if you are in two-dimensional space.
Okay, sir.
Yeah. So, so what we are trying to measure is how fast is the direction of normal is being changed. That gives us an idea of the curvature, intuitively speaking. And it actually is the, I mean, if you go very deep into maths, I mean, the differential geometry part, they prove it that it's the instantaneous rate of change of the direction at a given point. So, but here I hope the idea, intuition is clear that we are just trying to check how fast the direction changes. I mean, here we are checking the normals, but even if you see the tangents, since in the 2D space you can see you always have tangents perpendicular to normal, so it's the same. Measuring in the normal direction or in the tangent direction is the same. So now you have an idea of what curvature means, right?
Yes, sir.
Intuitively. Okay. So now what can we do? I mean, this is just an intuitive idea. We might want to move ahead of intuition. So, mm, what can we do? We'll try to. I mean, what did we do? We took. Sorry, yes, I deleted it. Yeah. So we took 2 points, right? Two adjacent points. From there we drew normals. Instead of that, we try to take 2 points. Yeah. So instead of that, we try to take exactly those 2 points and fix this normal out here, right? But in the other direction. So what are we doing? We took 2 points out here and then we fix this. normal and just reverted it in 180 degrees. So given this direction and these 2 points, we have a unique circle out here. Okay. So this is circle. And again here given these 2 points, adjacent points, which are arbitrarily close. And again we take one of the normal, just flip it back and then take a circle, right? So here the circle is pretty large. So do you agree that uh, this radius will be more of the circle of this, I mean the right circle?
Yes, sir.
Yeah, because here the points are almost, I mean they are pretty close to each other and they don't change the direction. So it's like the normals here will also not change the direction. So this circle will be of very large radius. But when it comes to this one, the left circle, since the direction here changes pretty quickly, the circle here will be small. So for generating a circle, you need three constraints. The three constraints that we use is the 2 points and one normal out here. So based on that, we are defining the circle. This is the center of the circle. So as you can clearly see that if the circle has smaller radius, you say that the curvature is high, and if the circle has larger radius, you say that the curvature is low. Yes, exactly for the same point. It's claimed, right? The curvature is low
Yes, sir.
intuitively. Here the curvature is high, but as you see that if the curvature is high, the radius is low. If the curvature is low, the radius of the circle is high. Yes. So that
Yes, sir.
means k, or rather kappa. People generally call it as kappa. The Greek letter kappa is inversely, rather exactly inverse of the radius of the circle, which fits at that point. So this is how intuitively you could define the radius, so the curvature at any given point on a curve. Okay. So given all these things, and there were a few explanations in the lectures. Yeah, why do we need all this first form and second fundamental form? Is because we ultimately need to find the curvature at any given point of time. Sorry, at any given point on the surface to characterize that point. So these fundamental forms together gives us a really nice way of defining the curvature, as you have seen with the linear form and then mean curvature or the Gaussian curvature. Once you define these fundamental forms and get those specific coefficients, you are easily able to find the curvature of the surface at any given point. So that's why we need this first fundamental form and second fundamental form. Okay, given that we just tried to understand why do we need this? Maybe just let's solve it. So, given that our notations in the class were capital X, so I'll keep it here as capital X. So, our parametric surface is u, v, u comma v. Okay, let's start solving the question. X of u, v is, so the first two are the same. And what else do we have? With u is t square and v is ut. So, we are given these relations. Okay. So, what does this mean? This ultimately this x is dependent on t, right?
Yes, sir.
Because x is dependent on u and v, and u and v are dependent on t. So ultimately x is only function of single variable. Given that we have these two uh, u and v relations. Okay. So what is it that we need to find? First fundamental form coefficients at t equals to 2. So if you remember correctly, E, we need to find E, F, and G, which are the coefficients of first fundamental form. Okay, and if you simply try to solve, I mean, yeah. So this was derived in the class about these specific formulas, I mean, which are pretty straightforward. They are just taking the squares. F is xu xv. Yeah. G is xv xv. What do you mean by xu and xv? So xu is partial derivative of x with respect to u.
U.
Yeah, that's how it's defined. Yeah. So okay. So just take the partial derivatives in what in each of the elements. So we have del by del u. Here is uv. Here is uv. Given this, what's out there? One. This is zero, and this is v. Right?
Yes, sir.
Yeah. So okay, and xv is del of x uv upon del v. So I'm just writing it out explicitly so that there is no confusion in terms of notations. Once notations are clear, then this is pretty easy. And yeah, del by del v of uv. Okay, so this is what I wrote it wrong.
01 U.
Yeah, exactly. This is 0, 1, and this is u. Okay, fine. So this at t equals to what? 2, right? Yeah. Given that we need to find t equals to 2 with v equals to 2t and u equals to t square. Okay. This turns out to be v equals to 2t, right?
104.
104, and this will be this set t equals to 2 will be 0, 1. This is t square, so it's 2 square is 4. Okay. So we got the values for xu and xv at t equals to 2. Now what is there left? What's left out there? E equals to xu. Take the dot product of xu with itself, which is what? 17. F is xu into xv, which is 16, and g is xv into xv, which is again 17. So this is the answer. Any doubts computing the coefficients of the first fundamental form?
No doubt, sir.
Okay, yeah. Okay. So yeah, we move on to the next question. I guess this should deal with. Okay, yeah, it deals with both first and second fundamental form. Okay. Um, yep. So given, oh yeah, given everything, given EFG, the coefficients of first fundamental form, and small e, small f, small g from the second fundamental form, we need to find the Gaussian curvature. So just for revision, I'll write out the explicit form E F F G inverse. So this is the linear form, linear map. They specified a linear map, right? Linear form. Yeah, in the lectures it's given as linear map. So given this matrix, which is let's call it as A, matrix defined by the second fundamental form coefficients and the first fundamental form coefficients, we will try to get we get the two curvatures, which is the Gaussian curvature and the mean curvature out here. So if you explicitly write out the formulas, then it's easy to solve it. So I'm just directly writing out the formula for Gaussian curvature. Well, it's just a 2 cross 2 matrix. You can just try to invert it and multiply it. So the Gaussian curvature is what? It is the multiplication of the principal curvatures, right? K1, K2 are principal curvatures, which is nothing but the eigen eigenvalue, yeah, eigenvalues of this matrix A. So multiplication of eigenvalues is again just the determinant of the matrix, right? Yes, no,
Yes, sir.
yeah. So these are coming
Eigenvalues.
from the linear algebra basics. These are the eigenvalues of A, which is just the determinant of A. So since you have the values, you can just place it out here. E is 1, G is 1, F is 0. So it will be 1 minus 0 on top. And then the second is E1, F2, G3. Okay. So this is 3 minus 2 squared. It's 4. It is minus 1. Okay. Is this question clear?
Yes, sir.
So it's just applying formula, nothing much about it. But yeah, we should try to understand that Gaussian curvature is the multiplication of the principal curvatures, which is nothing but just the eigenvalues of the linear map, and multiplication of any eigenvalues is nothing but the determinant of A that's coming from linear algebra. Okay, now move on to the next question. Okay, since we computed the Gaussian curvature, so next question is on mean curvature. It's exactly the same values. Okay, so we need to find the mean curvature given EFGs of both the first and second form. What's the formula for mean curvature?
K1 K2 by K1 plus K2.
Yeah, so it's the, you can say it as the, I mean, it's the mean curvature as it says, which is just the average of eigenvalues of A. So it's well known that what do you give, what do you get by getting the summation of eigenvalues? It's a trace, right?
Yes, sir. Trace
K1,
is the sum of all the diagonal elements, right, sir?
yeah. So K1 plus K2 since they are eigenvalues of A, K1 K2 since they are eigenvalues of A, so the sum of all the eigenvalues is determined by the trace of that matrix. So instead of computing K1 K2, I mean explicitly computing K1 K2, if you just know the elements of this matrix explicitly, you can write the trace expression. You can write the A properly and then just get the diagonal elements and then sum it. So which leads us to this specific form of So again, it's nothing, just placing the values. G, okay. So this is two times two. This is zero. This turns out to be 4 upon minus 2. This is minus 2. Okay, so the mean curvature is minus 2, and the Gaussian curvature is minus 1. Can you guess what kind of curve it will be? So you would have checked different types of curves, right? In one of the slides.
Yes, sir. Both are less than 0.
Yeah, both are less than 0. So might look something like this. Okay. So yeah, so it's same as that of Saddle Ridge. Correct me if I'm wrong. I think it's the Saddle Ridge. Yeah. For Saddle Ridge, h is less than 0, k is less than 0, and given that, so given these two things, since multiplication is less than 0, multiplication is less than 0. Okay.
No, sir. Multiplication will be positive.
But k is less than 0, right? Gaussian curvature is less than 0. K is minus 1. K is minus 1 and h is minus 2. So it's the Saddle Ridge. It's fine. I mean, okay, yeah. I'm confusing the notation. Okay. So what does this mean? So h of k1 plus k2 by 2 is less than 0, which means k1 is less than minus k2, right? And k1, k2 is less than 0. And given that k1 is less than minus k2, what can you say? K2, k2 is less than minus of k1. Okay. So if I assume k1 is greater than 0, then k2 is less than minus of k1, right? Minus of k1 is anyways less than 0. Yes, right? Is this computation clear? So we have these two expressions coming from the two curvature relations, right? Yes, no. This is h, right? And this is what, k. Am I audible?
Yes, sir. Yes, sir.
Yeah, okay. So given that we have h and k like this, I'm just trying to rewrite it in this way. So if you have k1 greater than 0, then k2 is surely less than 0. So what does it mean? So k1 is greater than 0. Greater than 0 means you can think of it as minima, right? And k2 is less than 0 means there is some maxima. So your curve will go something like this. So if maybe I just draw it like this. So your principal curvatures are coming like this. This is the maxima one, K1. Oh, this is the maxima one, so it is K2, which is less than 0. And this is the minima one, which is K1 is greater than 0. So your curve will look like this. So this is the whole surface out here. And backside will look like this. Do you get it? I mean, it's like half cut pipe, but it's tilted in such a way that this is going upwards, this part is going upwards, and here the curves are going down. Is this one clear?
Uh, so that is the curve we find in the image, sir.
So I mean, yeah, this specific relations, I mean, this E, F, and G will lead us to some curve like this,
Okay.
locally speaking. So if this is the center, if this point is the center, then the curve will look something like this. So in one of the directions, it will be like minima, where k1 is positive, and in the other direction, where k2 is negative, this will be the maximum. And the directions are given by what? The eigenvectors, right?
Yes, sir.
These directions are given by eigenvectors. These are the corresponding eigenvalues, and based on that, you can just approximately know what this curve means here. I mean, how is the curvature at this specific point? So I mean, this is the whole reason why we are trying to compute all these things. We are just trying to find the local geometry. Local geometry means how the curve varies given a point. So given k1 and k2, we can just get an intuitive idea like this. Well, it's not intuitive. I mean, it's the correct idea actually.
Okay, sir.
Yeah. Okay. I guess this question is pretty simple, but I hope you are able to understand the idea behind it. Why are we doing this? Otherwise, I think this just formulas. Okay, this one is more about understanding of the acquisition process. Which of the following are examples of passive imaging? What is passive imaging? Passive imaging, active imaging. I guess active imaging was defined in these lectures, the first lecture of this week, week 9. So it's just the opposite. What is active imaging?
Regular image.
Mm-mm. No. You're talking about active imaging? Regular image?
Yes, sir.
No.
Passive image is the depth of.
No, no.
Okay.
So what is active and what is passive out there? So if you remember class 11th, 12th physics, what are active circuits and passive circuits? I mean, a similar analogy can be kept here. So if there is an voltage source or a current source in the circuit, right? We call it as an active circuit. Yes. And if we don't have any voltage or current source, I mean, there is no source, there are only dissipators like resistors, capacitors, inductors, then you have a passive circuit. Similarly, active here means we have an active source of energy for light. Light, I mean light in general, not just the visible light. We have infrared, IR, base sensors, and all. So they push out some pulse of light out there, and then whatever is received back based on that, they are trying to get the image. So that's how the range imaging works, right? the basic idea of range imaging is clear.
Yes, sir, clear.
Yeah. So yeah, you push out a laser or some other infrared kind of beam, and then wait for how much time it takes to come back, and then based on that we get the estimate of depth. So that's the first one, time of flight sensor. So since time of flight means we are actively sending out some pulses out there based on, I mean, mostly lasers. So it's an active source. So it's an active imaging. Triangulation based sensors, if you remember, again we push out a laser from from one
Yes, sir.
camera, and then sorry, from one source, and then there is one camera out there. So again, since you are using some pulses, so it's active source. I mean, we have an active source, and so it's an active imaging case. Structured light, what do you do in structured light? In structured light, we throw a random dot pattern, right? And then based on the local area, we say that it is that random dot pattern is unique.
Yes, sir.
Yeah, so
Sounds
again we
good.
are throwing some pulses out there. It's not a pulse here, rather it's just a single, just a bunch of rays, not continuous beam of rays. It's just bunch of rays, and then take a picture of that specific rays. Probably it's in, mostly it's in IR range, and then you you get the estimate of the depth based on the unique
And
patches. Yeah.
same as natural light, sir.
Sorry.
Same as natural light.
Same as natural light? No, here structured light will be, I mean, you are specifically putting a pattern out there on the object. It's
Okay.
not same as natural light. So when you put a specific pattern on that object, it uniquely identifies each patch in that object. So once that patch is identified uniquely, you can match it from other uh, camera. So based on matching, again you can easily get the depth out there. So here structured light is also active. If you remember Kinect sensor that was discussed in the class, Microsoft Kinect sensor. So that's the version 1 is an example of structured light. Version 2 uses the time of flight sensors. Okay, stereo
Perfect,
imaging.
sir.
What is stereo imaging? What did we discuss?
We use of two camera
Use
centers.
of just two cameras. There is no light
Yes,
source
sir. Yes, sir.
that we put it. Whatever is coming from sunlight, it's out there. That's all. So
Passive.
yeah. So it's this is passive. So with these examples, I hope it is pretty much clear on what is active and what is
Yes,
passive.
sir.
And I hope that electrical circuit example was useless. I guess no one recognized it. Mm, yeah, but anyways, that's how the nomenclature works. Active means there is an energy source, and passive means there is no energy source, whichever domain you are working. Okay. Hmm. Okay. Some differential stuff. So we are given again a curve. Here it's denoted by capital Z, U, V, and the parameters are U and V for that curve. Which of the following is the fundamental form for the graph? Okay, I think this part is not relevant. We just need fundamental form of Z, or rather for Z. For Z. Okay. So how do you compute fundamental forms? By now it should be a cakewalk. Just putting up formulas, right?
Yes, sir.
Yeah. So what we'll do first, compute the partial derivative with respect to u. We have 2u, v, and 3u, which turns out to be 2, 0, 3, v. correct?
Yes, sir.
Okay. And ZV is del by U, UV of del V. Okay. Which turns out to be 0, 1, 3. So what we need to find these coefficients. Okay. X, or rather we are using Z here. So ZU dot of ZU, which is 2 plus 2 square is 4 plus 9V square. F is ZU dot ZV, which is what, 9UV. G is ZV dot of ZV, which is 1 plus 9V square. So you got E, F, and G, and this is for du square, right? This is the coefficient for du square. Coefficient for du square, this is du dv, and this is dv square. Or in the notations as used in the lectures, it is u dash, u double dash. I guess this is u dash, v dash, and this is v double dash of t. Maybe I'll just remove t for now. Okay. So for du square, it is 4 plus 9v square. So we have two options out here, and then 9uv plus 1 plus 9v square. Okay, there's something wrong. So the correct answer is not in the option, but yeah, this should be 9v square. Oh, sorry. This is, I did a mistake. Here it's 9u square.
Yes, sir.
Yeah, yeah. Okay. So this is the correct one. This is 4 plus 9v square du plus 9uv. Yeah. Du dv and 1 plus 9u square dv square. Okay. Any doubts in this one? We just need to make sure that which are the coefficients. I mean, coefficients corresponding to what. That's all there is to it. Nothing more. Okay. We'll move on to the next question. Okay, I guess this is the easiest one for the day. Consider a set of parametric equations. It's x cubed, by the way. This is x. Let me see. Yeah, it's x cubed. Sorry, t cube. X is t cube plus 2t, and y is 3t minus 2, representing a 2D curve. So we need to compute the tangent vector x dash t, y dash t at t equals to 2. So I think it's pretty simple. X dash t is what? 3t
3t square
square
plus
plus
2,
2. Yeah, it's 3t square plus 2. Y dash t
3,
is 3. And if we put at t equals to 2, this is what?
14,
This is 14, and this is 3.
3.
So yeah, that's the answer. 14 comma 3. This is the tangent vector at t equals to 2. Okay. I guess we have moved on to the next topic. Yes. The next topic that we were, I mean, that was discussed in the lectures was about edge detection, and not the usual edge detection that we have seen in normal images, but here it's specific for the range images. So, what is roof edge and what is step edge? I mean, the names are quite intuitive if you use it from the general English form. How does a roof of a house look like? Old houses, rather. If this
And
is
there would be some like point
like this.
corner. Yes, sir.
Yeah, I mean, that time the main idea was that if water falls, then it won't be stagnant out there. So that's why it's called as roof edge, because it looks like the roof of the house. And what is step edge? What is step edge? There is a steps in the stairs. So every day we either climb up or down the stairs, right? So
Yes,
this
sir.
is the
Step.
step edge. So these are general English words. They are just used it here. These are easy tricks to just remember these things. Okay. So we now know what is roof edge and what is step edge. So what do we need to check first? Okay, we'll first check the statements. Roof edge points are detected from zero crossings of the Gaussian curvature. Yes or no? Okay, which one of roof or step edge is determined from zero crossings? Given these two graphs, it should be very intuitive.
Roof.
Why?
Because there is some corner over there. So
What do you mean by zero crossings? So this is some function. Just some a, and this is some function f of a. Okay. So if this function goes like this, then these 2 points are zero crossings, right?
yes, sir.
These are zero crossings. So here I did not define the y-axis, but if your y-axis is here, I mean, if your x-axis is here, that means y equals to 0 is here. That means your coordinate system will be somewhere like this, right? So this step edge can be detected from zero crossings of the Gaussian curvature.
Okay, sir.
Yeah. And what about the roof edge? Roof edge will be from the extrema of the dominant principal curve. See, these whatever diagrams that you're seeing, these are in what, one dimension, right? It's only varying in x, and whatever the other dimension is, it's just the value out there. But whatever we are discussing here, Gaussian curvature, principal curvature, and all, they are, I mean, they vary in two dimensions, u and v, for instance, and the third one is the actual curve out there. So intuitively speaking, if you put it back to this space where it's only varying in one direction, you can see that here for the case of step edge, you can keep your y equals to 0 out here and then check for the zero crossings out here. And for the roof edge, what does it do? You're trying to find some maxima out here, right? So
Yes, sir.
this maxima gives us some edge out there in the higher dimension. So these are the intuitive explanations. And Of course, now we need to be careful about this thing. Which of the following statements are not true? Okay, so let me first point out what is true. Roof edge points are detected from zero crossings. No, this is true. Step edge points are detected by zero crossings, which is true, and roof edge points are detected by. So this is true. So your answer would be A and C, right? Any
Yes,
doubts?
sir.
Okay, why is it not selected? Okay, sorry about this. Okay, yeah, I think there's something wrong. Okay, let me see. Okay, fine. Let's move on to the next question. I don't know whether you people are getting anything from today's lecture or not. I think
Yes,
it's
sir. Able to understand something.
okay. I mean, it's going slow, and then I don't know how useful are these things. What I'm explaining. Okay. So the following statements are true regarding the surface types considering the signs of their curvatures K1 and K2. Okay. So I guess now we can do some visualization part out here, as it was quite boring out there. So we'll first look at the peak surface. How does peak surface look? It's like peak of something, right?
Yes, sir. Freak.
Loosely speaking. So everything is just simple plain English out here. So based on that, so since we are in three dimensions, we'll only, I mean, the two dimensions are the independent dimensions. So it looks something like this. So I'll try to draw the principal directions, probably. Assuming that the center is the place where we are trying to check the curvature. Okay. So probably this could be K1 and this could be K2. Okay. So what do you think, given this curve, what should be the values of K1 and K2? K1 is like a maxima, right?
Yes, sir.
So it will be less than 0. So I hope you are getting this analogy from the high school basics that was also given in the class. So if you take the second derivative out here at this point, what will it be? Second derivative will be what? I have some function f of x versus x, and I have a point out here and another point out here. So what would be the second derivative out here? Let this be x1 and let this be x2. Okay. So f double dash at x1 will be less than 0. F double dash at x2 will be greater than 0. So if you remember any of these criterias for maxima and minima, f dash at x1 is 0, right? So at these 2 points, the derivative will be 0, and based on the second derivative, we decide whether it's a maxima or a minima. Yes, no.
Yes, sir.
So yeah, that's the whole thing that we are trying to give an analogy out here. It's not
Okay.
exactly same that we are trying to find a maximum or minimum, but here k1 and k2 are the representative of the first and second, sorry, second derivative out here. So based on that, we are trying to make a guess how good, I mean, how the curve, the surface looks like. So as you can see here, k, I mean, for maxima the k is, I mean, rather the second derivative is less than zero. For minima, the second derivative is greater than zero. So here for peak surface, both of in both the directions, it should be the maxima. It's a peak surface. So that means k1 is less than 0 and k2 is less than 0.
K to zero. Yes, sir.
So given these two things, what do you say? Peak surface, if both k1 and k2 are negative, is it right?
Yes, sir. Right.
Okay, nice. Next, the next. Saddle surface. What is saddle surface? Have you ever heard of saddle points in school somewhere? Not in
Yes, sir.
school, at least in college. Okay. What are they?
Something like U shape, like bowl shape.
U-shaped and what? Okay. Let me give you a better example. How does the graph of x cube looks? If this is x and this is x cube, how does the graph of x cube looks? Okay. My drawing is pretty bad. Looks something like this, right?
Yes, sir.
So yeah, so so this is actually a saddle point. Saddle point, but I mean the here the saddle point definition is different. I won't go into those details. The problem here is we have a surface. Okay, so since we'll first draw the principal directions and then try to get what that surface is. So the saddle surface means in one of the directions it is a maxima and the other direction it is a minima. Okay, so here if you see both the directions they are maxima, right?
Yes, sir.
Yeah, so
Maximum.
here in one of the directions, probably a simplistic case would be maybe in x direction it is a maxima, but in y direction it's a minima. So the curve will look pretty complicated. I don't know how to draw it. My diagrams are pretty bad. So here it will keep on increasing, and then in this direction it will keep on decreasing. Somewhere in the middle it would be like this. Okay. It's increasing here, and then it's decreasing, decreasing here, and then it is increasing. Something like this. Okay. Oh, I drew the opposite direction. It's maxima in this side, right? So what can be done is I'm just trying to fix 4 points since it's maxima in this direction. So I'll draw two curves like this, and it's increasing in these two directions. So I'll draw two curves like this. Yeah, and given this, I'll just try to fix the other ones. Okay, so it is now clear, I guess, that in this direction it is going, it is the maxima, but in this direction it is some minima out there, right?
Yes, sir.
So what does
Yes.
this mean? So for this direction, if I call it as k1, and in this direction, if I call it as k2, then what? K1 is greater than 0 or less than 0. Maxima is less than 0, right? And k2 is greater than 0. Do you agree with this? Given that I drew this
Yes,
diagram,
sir.
although it's pretty bad representation, but I hope you're getting it. So it's a
Yes, sir.
curve like
Clear.
this, I mean, which increases in this direction, but if you go in this direction, it decreases. So this is a saddle surface, and this specific point is called a saddle point. Even in, I mean, even mathematically speaking, it's not any jargon out there. Okay, so what did we conclude, that the two principal curvatures are of opposite signs? Okay, so given this saddle surface, if both k1 and k2 are positive, this is wrong.
False.
Yeah, this is wrong. So what is ridge? What is ridge? Have you seen any ridge? So drawing a ridge is easy. I don't need principal curvatures for that. So I'll directly draw it, and then I'll draw the principal curvature. So okay, I guess I should go to some drawing classes first before teaching this. Anyways, yeah. So this is like a ridge where if I go for the principal direction, this is one of the principal direction, and the other one is this principal direction. Okay, if I call this one as k1 and this one as k2, what do you think k1 will be? So in k1 there is a maxima, right?
Yes, sir. Less than zero.
And k2, it's a flat region.
Flat region equals to zero.
Equals to 0. So of course now no one is saying that this should be k1 and this should be k2, so you can swap it. uh, so what is it? Grid surface, if any one of k1 or k2 is 0 and the other is negative, so one of them is
True.
0, another is negative. Correct. So this is right. So the last one is pit. Okay, what's the opposite of ridge if we're going to pit? It's like there is some sort of bump out there, right? If you invert the bump, it will look like something like this. There will be a valley. So this is valley surface. So again in valley surface, if you see that we have principal directions like this, and if you compute mathematically, these are the principal directions. Don't just think that I'm giving you an example. These are the principal directions for the for the curvatures. Okay. So what do you think here? It could be the same, right? Just one opposite thing. If I say now that keep the same convention, this is k1 and this is k2, and
K1
k1 is
greater than
k1
zero
greater
and
than 0, k2 is 0.
K2 equal to zero.
Okay, the last one is the pit surface. So go to that. Pit surface. How does a pit surface look like? This is even another. I need the principal curves. So, pit surface is the opposite of peak surface. I may not need it. So it will look something like this. What was peak surface? So for both the principal directions, we had maxima, right?
Yes, sir. Here
Yeah,
both will be
here
minimum.
both will have minima. So now you know the answer as well, I guess. But still, I'll explain it. Okay, this is some direction k1, this is some direction k2. So k1 should be
Greater than zero.
greater than 0, k2 should be
Greater than zero.
greater than 0. And what was the question out there? Both k1 and k2 are negative, so it is false, right?
Yes, sir.
Okay, so just one small exercise. Given k1 and k2 out there, what can you say about h? H is just the average of these two, right? H is greater than 0.
Yes, sir.
K is also greater than 0.
Greater than zero.
For this case, H is
Greater than zero. And
and K is
K is zero.
0.
Product rate, sir.
Here H is less than 0. Average, right?
Yes, sir. K equals to
K equals to 0. What about this?
H
H is
is less than zero.
why? I
One
did
is
not specify.
positive, another is
Yeah, I did not specify which one is bigger than other, right? So
okay.
H is something we don't know, but K is
K is negative. Product
K is
rate.
negative for sure. Yeah, K is negative for sure. Yeah. Okay. What about this one? Here H is what?
Negative.
Negative, and K is
K is positive.
yeah. And if you go and check back slides, these are the exact values that you would that was mentioned in the slides. Peak surface for peak surface H is less than 0, K is greater than 0, and similarly for others as well. So we actually derived H and K for different surfaces, although not all, but
Yes, sir.
hopefully now there is a geometric understanding of what these things even mean.
Yes, sir. Very clear understanding.
Okay. If you have more clear understanding than me, then please let me know.
No, sir. That F double dash of X, I was like, I was able to understand more because of that.
Okay. Okay. That's fine. Anyways, that was some analogy that was given in the class. Okay. Any doubts from today's session? Okay. I'll stop the recording then.